Hello, today we'll finally be moving into the next topic of the derivative function and the rules of differentiation. This is a very big unit in calculus, covering not only the derivative functions but various types of rules of differentiation that we'll get to cover in the later part of the lecture. So definitely we won't be able to finish everything today. So what we're going to be covering at exactly today's lecture is the smooth guidance into the realm of the derivative functions. We're going to define it. We're going to find what kind of identity that it has, what kind of characteristics that it has, what meaning or interpretation can it have, can it synthesize. And after we do that, we are going to learn there are a lot of types of the laws of differentiation, or also known as the rules of differentiation. However, since that is going to be taking way too long, we're just going to be covering just 3 or maybe 4 if we have sufficient time of the rules of differentiation. And the latter remaining rules of differentiation that we didn't cover today, we will be covering them in the next class. Okay, so let's start about the derivative function. So just as the name implies, the derivative means that it has been derived. It came from something, right? It's derived from something. So you should be able to know, or you should be able to kind of think or allude to that the derivative function is not a naturally existing function. However, it is more of an artificially made function by using another mean. And we'll get to cover more about that in a few moments. Although it might sound confusing right now, you will be directly able to understand after looking at this specific example. So, to help you guys more understand this abstract concept of the derivative function, I'm just going to be starting with a brief, however lucid example. So let's say I have a plane, and then this is a red chalk. I have a quadratic function. And the function is really simple. It's just a basic simple. Y equals fx. And let's say in the class time, the teacher asked us, guys, I want to find the instantaneous gradient or the differential coefficient at x equals 1 of this function y equals fx. Well, then what would be your answer? We've done this a lot of times, or this is pretty much very similar to us now, right? Very familiar to us. So if I were to find the instantaneous gradient at x equals 1, oh, I forgot to mention this is x squared. Yeah. So if I want to find the instantaneous gradient at x equals 1 of the quadratic function y equals x squared, then what do? Yeah, of course, the first principle is what we should use. So the first principle, since we did this so many times before, I'm not going to write the general formula. I'm just going to go straight on with the problem solving. So it is actually f1 plus h minus f1, right? The first principle formula. However, in replacement of f1 plus h, I'll just write this one more time. 1 plus h minus f1, right? However, instead of f1 plus h, if we actually plug in 1 plus h into place of x, then what is this going to give us? It's going to give us 1 plus h squared. I'm just going to expand it. 1 plus h squared is equal to h squared plus 2h plus 1 and minus f1. And what is f1 exactly? If you plug in 1 in y equals x squared, then you get 1. So basically, it'll be h squared plus 2h plus 1 minus 1 over h. However, since there is 1 minus 1, these are going to cancel out, and it is going to equal to just h and then h squared plus 2h, right? However, you can be able to see, if we look at this state right now, both the denominator and the numerator approaches 0 as h approaches 0. So therefore, if this is actually the case, then we won't be able to have a valid fixed solution. However, luckily, on the numerator, we also have a factor of h. Since we also have a factor of h, common factor of h on the numerator, we can factor them out. And then we can simplify the both h on both the denominator and the numerator. which will get rid of our factors that will result in 0 or non-existing solution for this limit equation. So therefore, we are sure that this limit will exist. So therefore, since h is approaching 0, you can plug in h here, which equals to 0 plus 2 equals to 2. So, although we have done this a lot of times before, we can say that f prime 1, or in other words, the instantaneous gradient at x equals 1 of the function y equals x squared is equal to 2. So I'll erase all these processes here. F prime 2 is equal to, f prime 1. F prime 1 is equal to 2. Then, congratulations, we solved the first one. However, this was the end. The teacher then subsequently asked the students, now I want to calculate the instantaneous gradient at x equals 2 of the same quadratic function y equals fx. Okay teacher, that sounds easy too. It wouldn't be that hard. We use the same mechanism, right? So when x equals 2, what are we trying to find? F prime 2. So how do we do this? Well, let's do it step by step. We also use the principle of the limits, right? First principle. However, I'll go much faster this time. So it's also h, however, over. On the top, it's going to be f2 plus h minus f2. However, just inputting that into the equation will give me h plus 2 squared minus f2 equals to 4. So minus f2 will equal to minus 4. Right? I'll expand this equation. H plus 2 squared. So it's a perfect square. This is going to be equal to h squared plus 4h plus 4 minus 4. So therefore, as the same case as the first one, the constant on the numerator will both be cancelled. So therefore, this is only going to result in limit as h approaches 0, h squared plus 4h over h. However, the numerator, just like the first case, also has a common factor of h in both factors. So I can pull out the common factor of h. And this is going to be h plus 4. And then if I simplify the 0 contributing factor on both the denominator and the numerator, I'm confident that this limit will exist. So therefore, since this limit exists, I'm pretty sure if we apply 0, if we input 0 into the place of h, as h is infinitely approaching 0, then it's going to be approaching to 0 plus 4, which is going to be equal to exactly 4. Okay, so we calculated the f prime 2, which is 4. F prime 2 equals to 4. Right now, I'm seeing a little bit of relationship, although I am not 100% sure right now. However, you can see that as x increased by 1, the f prime increased by 2, right? So I'm hypothesizing whether as x, the relationship between x and f prime will be as x approaches 1, f prime will increase by a factor of 2, or will be having a linear relationship by adding on 2 as x increases by 1 each. So let's see if either of my hypotheses are validated. So I had 2 hypotheses, right? So let's try the third one, and then I think this will be clear enough for us to see the pattern that has between x and the instantaneous gradient, also known as f prime. So I want to find the f prime 3 now. Although it's a little bit of tedious, this will be my last one calculating. So I'll use a little bit of more bigger space here. So first, also using the first principle mechanism, this is going to be f3 plus h minus f3. This is going to be equal to, if I plug in 3 plus h into place of x squared, then it's going to be h plus 3 squared minus, I'm going to input minus f3, right? Then if I input 3 into this equation, it's going to be 9, because it's going to be 3 squared. So therefore, if I re-evaluate this equation again, then what am I going to get? Well, let's say I expanded this equation. Then, well, it will be the same case as the first and the second try that we did to find the f prime 1 and f prime 2. The constant here will be equal to 9, so the constant will be subtracted from each other. That is only going to leave us the first 2 places that both includes h squared and h. And then if I evaluate this equation, it's going to, without the constant, then it's going to be equal to h squared plus 6h. However, they also have a common factor of h, so I'll be able to pull them out. I'll be able to extract them, and since it was originally h squared plus 6h, it's going to be h multiplied by h plus 6. And also, same, I know it's tedious, but the zero contributing factor in both denominator and numerator has been removed. So therefore, I'm very confident that this limit will exist. And since 0 plus 6 is equal to exactly 6, I can see that the f prime 3 is exactly equal to 6. So, what kind of relationship do you see? Was either of my hypotheses correct? Well, if you look closely here, as x increased by 1, f prime also increased by 1. However, from the second to third relationship here, as x also further increased by 1, f prime, rather than increasing by a factor of 2, also increased by just 2. So in this both cases, we can see as x is increasing by 1, y has increased by 2, showing a linear relationship with a gradient of 2. So therefore, let's say that I want to generalize this equation. What if x was equal to n? Then what would f prime be? Well, by considering this relation, I'm pretty sure that I can say that f prime n will be equal to 2n. Whew! Well, that's kind of like a magic, right? I've always thought that was a functional relationship between x and fx. However, I also did not know that there was a pattern. There could be a pattern that has been existing between x and the instantaneous gradient at that certain corresponding point of x. So this exact example here directly connects to our understanding and the identity of the derivative function. The function that you just see here, the pattern that you just made here, is known as the derivative function of this equation. So that's pretty surprising, right? That was a very smooth understanding, very smooth transition into the identity of the derivative function. So now do you get why it has a meaning of the derivative function? It is because the derivative function did not exist naturally. It cannot really be calculated just by visually, right? Just by looking at this function, you cannot get a grasp of what its derivative function is going to look like. Or just by looking at this mere quadratic function of y equals fx or x squared, you are not able to tell the relationship between x and its corresponding tangent or its corresponding value of instantaneous rate of change. Just by looking at this function, you're only able to recognize the relationship, the correlation between x and the y values, not x and f prime values, right? So therefore, we had to artificially analyze and come up with the pattern. Therefore, since we came up with this pattern by using the data on the original function of x and y values, that's why we call this new pattern the derivative function, since we garnered this information deriving from the original function. So this is what you can think of. This is the artificial pattern, artificial function that has been made from the original function. It has been derived from the original function, so that is why it is called the derivative function. That's pretty easy, right? Yeah, so this is the exact meaning of the derivative function. However, one thing that I want to emphasize here is I want to refer one more time back to the concepts of the limits and the instantaneous rate of change. I said that the instantaneous rate of change, let's say that I want to calculate f prime a, I won't be using the first principle equation, I'll be using the average rate of change equation with the limits for the instantaneous rate of change equation. So, just like the first principle equation, this is also the equation of the instantaneous rate of change, right? The instantaneous gradient. One thing that you have to be cautious when learning about the derivative function is, we have learned that when you're trying to find the instantaneous rate of change at x equals a, then x infinitely gets closer to a, right? However, I said that this limit of the instantaneous rate of change cannot exist if x is exactly equal to a, right? Then, because both the denominator and the numerator will be approaching 0, allowing it to have any kind of values, not converging into a one fixed value, right? So therefore, I said that x must be only infinitely getting closer to a for this instantaneous rate of change to be defined. However, by looking at the derivative function here, one thing that I forgot. So we call the derivative function f prime x. This is the derivative function that we call. So when you're trying to when you're comparing this value with the derivative function, although x cannot be exactly equal to a when we're trying to define the instantaneous gradient at x equals a, this symbol seems as like, this f prime a seems like x is exactly equal to a, right? So therefore, this is kind of a nuance. This is kind of a subtle different interpretation that these two concepts combine. These two concepts separately or discretely possess. So therefore, you should always understand, even though it is f prime a, you should always think that x is not exactly equal to a, however, is in a point where it is infinitely getting closer to a. One more conceptual thing that I wanted to emphasize. Yeah, that was just the difference between the first principles and the derivative function, what kind of difference that it contains, and also, just like I put it on the blue chalk here, so the derivative function, that the pattern that we found, a new pattern that we found, the relationship between the x coordinate, the x value, and the instantaneous rate of change, the instantaneous gradient corresponding to that x value, that correlation, we call it the derivative function, right? And just like that, we call the derivative function as equal to f prime x. And this f prime x, there is a specific way that we can calculate it. So what I'm trying to talk about here next is, we define f prime x as the derivative function, right? So in this case, this is going to be equal to 2x for this corresponding quadratic function, right? Just like the pattern that it said. However, there's going to be a lot of more types of function that we will have to find the derivative function of. That we have to find the derivative function of, such as like a cubic function, quartic function, trigonometric function, so many things else, right? So therefore, it is a good experiment and a methodology to check, to analyze the patterns directly by plugging into the numbers, by solving the f primes by the first principles, and trying to come up with a pattern that you can think, and then initially, artificially, hand-madely find the derivative function. However, I just want to say that this is very, very difficult to do. It is very time-consuming, and who knows what kind of pattern that it will give. For this typical equation, it gave a linear relationship. That was easy. However, what if we get like a cubic relationship or a quartic or quadratic relationship? That is going to be really, really hard to put it all into a place of numbers. So basically, we have to find a different way to find the derivative function of each types of function we get, right? And I will tell you the method to do that right now. So you remember that we first found the instantaneous rate of change. The instantaneous rate of change by using the concept of the first principles, right? By the concept of the first principles, so fx. I'll just write one more time. So f prime a that we wanted to find was calculated by the formula of the first principles. Right? However, now I want to calculate fx, f prime x, the derivative function. That's simple. Then I just have to change a to x and a to x. I just have to substitute the a by x's. And what kind of difference does this create? Well, f prime a was a fixed value, so we're trying to find the instantaneous gradient at a fixed point. However, in this case, all a's have been superseded or has been replaced or substituted by x. So what does this imply? We're trying to find the overall relationship between overall equation of x and f prime x. So this, although it is the exact same as the first principles, this is the equation that we use to find the derivative function of any types of functions. So let's say that I want to calculate yeah, let's see if using this method is correct to find the derivative function of the original quadratic function of y equals fx. So applying this equation, I'll solve for the derivative function of the quadratic function y equals fx to see if our pattern was correct or not. So fx plus h, in this place, now we put x plus h over to the power of 2 minus fx, which is equal to x squared. Then I'll evaluate further back into this equation. Expanding it will result in minus h squared. So this is the value that it will result in. However, by subtracting the two h squares, we're going to be left with just x squared plus 2xh over h. Oh, this is h squared because we already had x squared at the right side of 2xh. And then just like these cases that we had, we also have a common factor of both h's, which if I put them out, extract them, then it's going to be equal to h plus 2x. And then also the zero contributing factor on both the denominator and numerator has been eliminated so that h is approaching to 0. If I plug in 0 to h, then it's just going to be equal to 2x. fx equals 2x, which corresponds exactly congruent to our predicted pattern, showing the validity of this equation where we tried to find the derivative function from. So whenever you approach another types of difficult functions or complex functions, don't be scared to actually find the pattern by yourselves, but rather plug into the first principle formula to find their derivative function. However, the only key differences from the first principles is that you're not trying to find a simple instantaneous rate of changes, but you're actually trying to find the overall relationship between the x values and the instantaneous gradients, just like as if it is another artificially made function. Now you get the identity, right? Okay, sounds good. Okay, so even though we learned a new and a critical aspect of the derivative function, I still want to emphasize that using the first principle equation is even too tedious. So we said that calculating it, artificially creating a pattern and then coming up with their own pattern is already confusing. So that is why I provided the alternative and yet a better technique by using the first principle way, right? However, I'm saying that even that way is too tedious now. As you get more deeper and deeper into calculus, more types of difficult functions will come out. Logarithmic functions, rational functions. These type of functions are really, really complicated to solve by using a limit first principle equations. So that's why I'm saying that there is a better way that exists to facilitate and expedite your process of differentiating a function. So, I'll just write the formula of the derivative function one more time for your references, because we're going to be using this formula to find a more better way to derive the functions or differentiate the functions. So, since I said that this way was already too tedious, even though it was faster than this process, artificially making the process, I said that this process was easier. However, even this process is convoluted, is complex as well, right? So, what did the mathematicians think to actually mitigate or alleviate this problem? Well, what they thought was classify the cases of different identities of the variables into specific formats and then derive them. What I mean by deriving here is differentiating them. By differentiating them, I mean finding the derivative function. So that's another way that we express. So repeating one more time, the mathematicians have thought that rather let's make some specific differentiation rules, specific laws of differentiation, where we can easily, or just like a formula, calculate or differentiate a function without using this complex format, without this complex calculation of the first principle equation. So this law of differentiation, rules of differentiation, can be classified into, I believe, 8 parts. It just, there's no specifically chosen parts, designated parts, but I just made it. I just classified it into 8 parts. And then I think we're going to cover 3 or 4 if possible. I think the lecture is already getting a little long. So, you will get to know what I'm trying to express here. So, the first law of differentiation that I'll be talking about is trying to differentiate, trying to find the derivative function of x with an order of power. What if I differentiate this? This is connotation for the differentiation. So let's make a specific rule or formula to differentiate this thing. Because just like this here, let's say if I want to calculate the derivative function of y equals x squared or y equals x cubed, then I would have to plug it all into this complex first principle equation here to find its derivative function of x prime x. However, I don't want to do that. I want a more simpler way. So let's think about this. So how are we going to create more simplified formula for just targeted for x to the power of n type of equations or functions? Well, to find a shortcut to this specific target of equation, then we also use the process of the first principles. However, we use the generalized format here. We deem x to the power of n as a function because this is a generalized function, right? This is a generalized model. Oh, and I forgot to mention that n here only applies to a natural number. No, not a natural number, an integer. N is integer. So, we use the same format of the first principle, however, not for any specific designated function, but for the general function, so that we can come up with a general formulae. So, f x plus h to the power of n minus fx equal to xn. We deem this as a separate function, right? So now all we have to do is solve this equation. Well, this n can go up all the way to infinity, right? There's no specific equation that we can solve. However, if you use the concept of the binomial theorem, then you can. Well, you don't have to learn this. You don't have to know this. Just look at me solving. That's all you have to do. Just the result is what matters. This is not the expectation for you to solve at the high school level. So actually, if you use the concept of the binomial theorem, you don't have to understand this. You don't even need to understand this. There's an actual way to expand this type of equation. It is by using a concept of the binomial theorem. And then, bigger parentheses, x plus h to the power of m minus 1, m minus 1 plus x, just this plus x plus h to the power of m minus 2x plus x plus h m minus 3 x squared plus all the way to x to the power of m minus 1 and then closing parentheses. So this is x to the power of n minus 1. I'm sorry for the messiness. So you can see that this is just so ordered that the format that it forms if you expand this numerator equation by using a concept of the binomial theorem. So let's now try to evaluate this equation. Well, you can see that it's x plus h minus x, so the x's disappear, only leaving h. However, since there are both common factors of h on both the denominator and numerator, the zero contributing factors can both be simplified. Then it just leaves limit approaching to 0 and this whole equation. So what do we get from here? If h is equal to 0, right? Then if I evaluate this equation here, and it's going to be, since h is 0, it's going to be x to the power of m minus 2 multiplied by x, which is going to equal to x to the power of m minus 1. And this equation here is going to be x to the power of n minus 3 multiplied by x squared. And this is also going to be equal to x to the power of n minus 1. And if you keep adding these, the last equation you get is x to the power of n minus 1 also. So you can see on myriad types of factors that forms in the middle of this by expanding this equation, all of those individual small factors here, fragments here, are all equal to x to the power of n minus 1. So therefore, how many of these are formed? Well, if you calculate it, n of these are formed. So basically, since I already evaluated by the equation by inputting 0 for all the number of h's, I can just say that n of x to the power of n minus 1 are left. This leaves n of x to the power of n minus 1 are left. So this is the overall equation. So this is equal to the derivative function of x to the power of n, where n is an integer. So although it was a very long description, although it was a very complex description, do you understand now? Well, this f prime x is equal to n times n x to the power of n minus 1. When fx is equal to n to the power of n squared, x to the power of n is always equal to this format. So basically, whatever types of functions that you have that incorporates or that can be classified into x to the power of n, where n is an integer, then without applying to find the derivative function of that original equation, you don't have to plug it into the complex first principal equation. Rather, you can just plug it right into the equation here, where n is already known, right? Because you're given the question, right? So you just have to plug in the number of n, the value of n, then the derivative function will automatically come out. So that is why we use the rule of differentiation to facilitate the differentiating process, to facilitate or expedite the process to find the derivative function of the original function that you were given. As known, first principle is better than this equation. However, now you see why this equation, the rule of differentiation, stands way more efficient and advantageous than finding the derivative function by using the first principle formula, right? Definitely. Because this, we have to go through complex limit equations, we have to go through like myriads of complex computations. It's nonsense. However, this equation, plug in the numbers, that's it. So, by trying an example here, let's say I want to differentiate or find the derivative function of x to the 100th power. If I try to put this in, find the derivative function by putting this into the first principle equation, I can definitely solve it, but I don't want to deal with all those big number computation. So, why don't we use the rule of differentiation? If we differentiate this, then this classifies into the equation of x to the power of n, where n is an integer. So, since n is equal to 100, then the differentiated form of this will be equal to n 100 multiplied by x. And n minus 1, in this case, it is equal to 100 minus 1, which is equal to 99. So exactly from right here, we're able to calculate the derivative function of the original equation, which seemed very complicated, without even using the first principle equation. So there was no type of calculation you just had to do. All you had to do was plug in the numbers, all due to the smart, erudite rule of differentiation that you got here. So this was one of the three that we are going to cover today. So the first one was pretty long. However, the second and the third one is going to take way shorter. And before we move on, just emphasizing here, I said that n is integer, right? However, I just want to tell you that even if n is a real number, and well, if it's imaginary, then this wouldn't exist at all, right? However, if n was a real number, the results are still the same. So let's say that n was a fraction or a decimal, then the same rule still holds. However, there is a different way to prove that this equation is also valid or is also supported by the case when n is equal to a real number, any real number, right? So I will tell you that type of derivation after we learn the concepts of the differentiation of logarithmic functions, because proving for x to the power of n, differentiating x to the power of n when n is a real number requires some more in-depth concepts of the logarithmic functions and its process of differentiation. So I'll make sure to remember to insert that part, but from right now, you don't have to learn those processes. I'm just going to tell you in addition, but right here, just know that even if n is a real number, the same equation is still valid. Okay, moving on to the second equation. No more time stalling. So, what about the case when what about the case when x has a first power? Just x. What happens if we differentiate x? Well, I'm pretty silly to put this in a discrete equation, just this x, right? Well, although it seems simple, let's do it. Well, there's a lot of ways to prove this, right? So let's try both ways. I have two ways that I can think of. Well, the first way here, since x is also known as x to the power of 1, which also classifies into this category here, right? This first rule of differentiation. So, if I do this, then it's going to be equal to x1. If I differentiate it, will be equal to, since n is 1 here, 1 times x to the power of 0. Well, if any number has a power of 0, then it's going to be equal to 1. So therefore, it equals to 1, right? However, there's another way to prove it. If you're unsure of this process here, or if you couldn't think, well, for example, that x had a power of 1 and this could be classified into the first category of the rule of differentiation, there's another way that you can approach it from. I told you that this way here, by using the properties of the first principle, this is the most basic, right? This is the most cornerstone of everything that we are doing right now. So even this equation, even though we made it more advantageous and efficient, we still have to go through the process of the first principle equation. So when there is a process, when you are given a question to differentiate a certain equation, however, you're unsure whether how to do it or what kind of rules of differentiation that you should use, then you're always welcome to use the properties of the first principle, because this is where all the rules of differentiation will be derived from. So this never lies. There is no exceptions for this. Everything can be fallen into the category. Every kind of derivative function can be calculated by using the properties of the first principles. So let's use the property of the first principles here. Limit h approaches to 0, and let's say this is just a function, right? Function y equals x. Then h over, since the x and the y values are same with each other and y equals x, then fx plus h will be equal to x plus h minus fx is exactly equal to x, right? So it's going to be x. So then x and the x cancels out, leaving h over x. And since they're both the zero contributing factors, I can eliminate them, emphasizing one more time, I can eliminate them and leaving 1 over 1, which is a constant having no relation to do anything with the limit equation here. So this will just be equal to 1. So both cases you do, you'll be ending up with the same equation. So when you differentiate x, it's just going to be equal to 1. Okay, now last but not least, the third law of differentiation. We're going to be trying to differentiate a factor of constant. So a constant does not have a variable. It does not incorporate a variable of x. It is just a constant. However, what will happen if you differentiate it? Or if you try to find a derivative of this? Well, I'm not sure, right? Because this doesn't fall into the category of the first rule of differentiation. So the only thing I'm left with is the rule of the first principles. This never lies, so let's do this. I will use a red chalk here. So, limit h approaches to 0, and fx plus h minus fx. What is fx plus h? Well, it is also equal to c, because c does not have any variables. It is just c alone on any part of the x, right? Despite the x is 0 or infinite, it always has the y value of c, because it is a constant. And so therefore, fx will also be equal to just c. Then what will this be equal to? Well, c minus c, this is exactly equal to 0. Oh my god, then we have a problem here. We have a dilemma. Both the denominator and the numerator are approaching 0. Is that correct? Well, nah. This, I know, can be a very, very confusing thing. However, I just want everyone to think about this. Although they both seem like a zero, although the denominator and the numerator both seem like a zero, so seeming as if this limit cannot exist or converge it into a single fixed value, you have to understand that C and C are exactly same with each other, thus resulting in an exact zero, while H is not exactly zero, but is infinitely getting closer to zero, as if it is a zero. So we're trying to say that this is exact zero, and this not exact zero. So what is the difference here? Can we actually deem this H as a zero if it is not a zero? Well, we have a closer zero here, which is exactly a zero. So therefore, since the numerator is an exact zero while the denominator seems like it is a zero, but it is actually not. While it is not and actually approaching to zero, while numerator is exactly zero, by the rules of mathematics, if the numerator is zero, everything is equal to zero. So this is just going to be equal to zero. So when you find the derivative function of the constant, or in other words, when you differentiate or when you derive a constant, then it is always going to be equal to zero. Or in other words, the other way that you can approach this equation by using a visual factor. Let's draw a function of y equals to c, deeming that c is a positive number. So this is the value. This is the function of y equals c. However, I said the derivative function is determined by the relationship between the x and the instantaneous gradient of the corresponding values of x, right? So you can see that the f prime x is the relationship between x and its instantaneous gradient. However, when you look at this function, you can see that at every kind of point of x, the instantaneous gradient of this overall function never changes and is constant with a fixed value of zero. So therefore, when you are trying to find the derivative function, or the relationship between x and its corresponding instantaneous gradient, no matter at every point of x, its instant gradient is always equal to zero. So therefore, your derivative function will always have to be equal to y equals zero. Because in each of these x values, the instantaneous gradients are equal to zero, because as shown here, the overall graph is flat. It does not have an increment or decrement value such as in the quadratic function or a linear function, which has slopes and a gradient. However, in this case, the gradient is flat, is consistent with the value of zero. So therefore, the instantaneous gradient at each value of corresponding x will also be equal to zero, having to result in a derivative function of y equals zero. So despite what kind of constant that you have, even if the constant itself is zero, positive, or negative, any type of real number, your derivative function will always be equal to zero. So therefore, this concludes our top 3 types of rules of differentiation and the identity of the derivative function. However, you have to know the abstract identity of the derivative function, right? That the derivative function did not exist naturally. However, it is a combination. It is the consequence that resulted from the results that we've garnered to make an artificially in order to facilitate our process of finding the instantaneous rate of changes, because we did not want to use the confusing computations of the first principles. So by continuing with this method, by continuing with this philosophy, I'll be continuing on with the 4th rule of differentiation from our next lecture. Thank you so much.